Alright, just two quick reminders. One, your mastering homework is due tonight. And two, we'll do a group quiz on Friday. Okay. So today what we're going to do is we're going to talk about the reaction quotient and then talk about how do you calculate the equilibrium constant and how do you determine if you're at equilibrium. Or if you're not at equilibrium, where are you in a reaction scheme? So, the reaction quotient is given the big old letter Q. And so if I have this reaction, let's say I'm at equilibrium, I'm at equilibrium, which tells me about the equilibrium constant. So what do I put on the numerator of my fraction? Which letter, A or B? B. And what power do I raise it to? Little b. Then what do I put on the bottom? A to the A, right? Alright, so if I'm at equilibrium, right, that's what we did on Monday. That's what you had in your homework. You just plug those things in. The reaction quotient, which is given the big old letter Q, is also equal to that but the reaction quotient can be calculated at any point in the reaction. So the equilibrium constant only talks about equilibrium. Q, the reaction quotient, tells me about everything else. And then by comparing Q and K, you can figure out where you are in relationship to K. So by comparing Q and K, you can determine where in the reaction pathway you are. So if, for instance, these values are equal, where should I be in my reaction pathway? I'm at equilibrium. Let's say the value that you calculate for Q is greater than what you know K should be. If we know K should be 5, and this is now 7, which has gotten too big? The numerator or the denominator? Right, so if this is 5 and this is now 7, it is the numerator, right? The numerator has gotten bigger, so my fraction has gotten bigger. Right, so B, the concentration of B is greater than it would be at equilibrium. So if I have too much B, that should be double arrows, which direction should my reaction shift? Right, should left or back to reactants, right? If I have too much B, I either want to shift left or shift towards reactants. They mean the same thing. I'm not good at left and right, so I usually say shift back towards reactants. Or you do your little... Alright, so the reaction must shift left to get to a point where this is equal again. Yeah, there we go. Yes, the third case would be, now my Q is less than K, which must mean that, again, if this is 5 and now I have 3, I must have a bigger denominator because it's being divided by a bigger number. Which means I have too much A comparatively to where I want to be. Right? I want to be at equilibrium. In order to get there, I have to use up more A. Which means you need to tell your reaction to start making more products, shift right, or shift towards making more products. Alright, so then how about we do some practice problems with that. Let's see how this works out. Alright, so let's say I have this reaction. I have nitrogen dioxide, I'm missing a 2. There we go. 2 nitrogen dioxides are in equilibrium with dinitrogen tetroxide. The reaction has a known K, 170. And we're going to do some things to it to determine the Q. And then given this Q, which direction does the reaction need to shift? So let's say alright, so let's first write out what K should be. So, do I have a product or reactants in my fraction on the top? Products on top. Does it get an exponent? No, I mean it's 1. Alright, so then we put reactants down here. And what exponent does that guy need? 2. Alright, and they tell us that equals 107. Alright, so we're at a point where I know these concentrations. I know that N2O4 concentration is 1.5 times 10 to the negative fourth, and my nitrogen dioxide concentration is 2 times 10 to the negative fourth. I want to figure out where I'm at, so I'm going to determine what is Q. First. Yeah, that has to be given. Yeah. So I'm just picking some numbers, and then we're going to see if where we're at. Alright, so Q has the same equation as K. We can plug in what they told us. Alright, so if we are at the point of equilibrium, what should this value be? 170. Alright, so let's figure out what it actually is. Right, 1.5, negative fourth. Yeah, if you don't have your calculator out, it's going to be a calculator heavy day. So you're going to want it out. Is this value equal to K? It is not. Purposely, I picked a randomly big number. Alright. Is Q greater than or less than K? Okay. So I'm at a point that Q is greater than K. So what do I have too much of? Yep. we need to shift left. Right? It means there's way too much of this. So to get to where it's equal to 170, you have to shift back the other way. Let's do another one of those. Alright, so here's my reaction of iodine and chlorine reacting together to make two iodine-chlorine combos. I know the K of this reaction, and I know I'm at a point where these are true. I want to know if we are at equilibrium. Alright, so, right, we got to start off with Q. If I don't know where we're at, we use Q. What should be in the numerator, the products of the reactants? Okay. And what exponents does the product get? Okay. Then reactants go down here. Then we plug in what they told us. So it's going to be 0.355 squared, 0.114 times 0.102. Are we at equilibrium? No. Okay. Is our Q greater than or less than K? No. Less than K, so what do I have too much of? I have too many reactants, right? Which direction do I need to shift my reaction? To the right. Yeah. Oh, yeah, so Q and K are unitless, so regardless of how funky the units are, they're just unitless. Yeah, because they wouldn't cancel really nicely. Okay, good there. Just plugging things in, comparing the two numbers. Alright, so that all leads us to talking about K, right? So the thing about K is that it only happens at one point in your reaction. Only at equilibrium. So in order to figure out what the equilibrium concentrations are, we have to do some math manipulation. See, that was funny. So, we always know the initial concentrations, right? You always know what you put in your beaker to get started. But you don't always know the equilibrium concentrations. But we can get there if you know your balanced chemical equation. So exciting, 3 exclamation points. I do love a good balanced chemical equation. Alright, so let's take a look at this. Oh, that should be mole. Alright, so let's say I have a reaction. So I'm saying butane turns into isobutane, which doesn't even matter what that looks like. If you took organic, you can certainly draw it. I'm just going to leave it labeled like this. Alright, so I gave us some information about butane. I want to know first thing we're going to want to know, well, first thing, like step 0, is right balanced chemical equation. That's really step 0. Step 1, once we've done that, is we need to figure out the molarity of the butane. How do I go about figuring out the molarity of butane from the word problem? Yep. So they told us we had 0.017 moles. And then what do I need to do to those milliliters? Convert to liters. Okay. So what we're going to do is we're going to construct what's called an ice chart. Because you always know your initial concentration. At some point there's going to be a change in concentration as the reaction proceeds, right? As the reaction proceeds, the reactants will go away, the products will appear, and then at some point you'll get to a point called equilibrium. So it's called an ice chart because we're going to look at these 3 points along the reaction, because we have to end up here, because otherwise that's the only thing we know, right? We know K. And so if we know K, we can kind of back calculate what these concentrations must be. All right. So the next thing we want to do is we want to write the K for this reaction. Right, so just like we've done a billion times, right? Iso is going to be products over reactants. So isobutane over butane. And I know that equals 2.5. But do I know anything about the equilibrium concentrations currently? I do not. I do know the following, though. So, at the initial, we have 0.34 molarity of that. If I put butane into a beaker, do I have any isobutane when I get started? No. I don't have any of that. They're called an ice chart. They're really more of an ice table. There's no charting. But either way. All right. So as this reaction proceeds, if I lose some amount X, where does that X go? To the product, right? So if it goes to the product, how do I show that it went to the product? Plus X. Right? So everything I lost from the butane, well, it must become isobutane. So those values must be equal. Good so far? So if I'm at equilibrium, it must be the point at which that's true. And then that must be true. You can put 0 plus X. That makes it more clear. Alright, so as procedure, right, initially I had this. It lost some. So I have a new concentration at equilibrium. Whatever this guy lost, this guy must have gained. So now I have values I can plug into my K equation. So the concentration of isobutane, according to my chart, at equilibrium is equal to X. And then what is my concentration of regular butane at equilibrium? Well, now it's just some algebraic rearrangement, and we can solve for x. So that's a good first step if I want to start to solve for x. Right? Multiply the denominator over here. Alright, what do I now need to do to get the x's by themselves? I see, yep, factor it out, right? Multiply this by this and this by this. So that's 2.5 times 0.34. So the rest of the semester is going to be a lot of algebraic rearrangement like this. Alright, so now what do I do to get the x's by themselves? Now I'm going to add 2.5 to both sides, so now 3.5. Last step, what do I need to do? Divide both sides by 3.5. And that should be... Alright, looking back at my chart, what is that the equilibrium concentration of? I now solve for x. So x refers to the concentration of isobutane. So then what is the concentration of butane? Alright, so based on my chart, 0.34 minus 0.24. Now we've answered the question. The concentration of both those species is equilibrium. Done. Alright, let's do like about 100 more. Alright, we're not quite ready for this example yet. We're not ready. That's the challenge problem for today. We're not ready for that one. We'll do that one. We'll do 2 more boring ones, then we'll work up to a challenge. Yeah? No, because it's rounding, because of the way that we truncated our significant figures. Alright, let's see. What do I got? Alright, so let's add this reaction. And initially you have that's not right, the brackets go around it. It's going to be a variation on the one we just did. In this case, I know the equilibrium concentrations. We want to find K. Alright, so last time we didn't know equilibrium concentrations, but we did know K. This time we don't know K, but we know the equilibrium concentration. Alright, so you can do it in either order. Let's do our ice chart first. And then we'll set up what K is equal to. Alright, so they gave us the initial concentrations. I like this one because it's a little tricky, but not too tricky. Alright, for change is going to refer to how many moles of things have moved, or how much molarity. Right, so in the previous one, the butane and isobutane were 1 to 1. Right, so if butane lost, isobutane gained. Now I have more than one reactant, and they're not all 1 to 1 to 1. Right, it's 1 to 2 to 1. So if I say this is going to lose some value X, how much of B should be lost? 2X, right? Twice as much, because I need 2 times B compared to this to make my balanced chemical equation work. So then what should happen to C? How many C's? 1, 2, 8, 42, 36. Just one. I'm just messing with you guys. Just one. Alright. But now, equilibrium, I know some things about equilibrium. They told me that the concentration of this is that. And they told me the concentration of C. So, what do I know about the value of X then? Yeah, right? You could figure it out either way. You could do what's the difference here or what's the difference here. Right, so if I started up at 0.3, I ended up at 0.45. How much must have X been? 0.15. If I'm going to lose 2 X's, it's going to be 2 times 0.15. That's 0.3. So then what must be the equilibrium concentration of this? Alright, so this, because I know this, that must be X. Or you could do it over here. Great. Yes, that's where it came from. Yep. So if it's 0.15 is X, 2 times X then would be 0.3. 0.9 minus 0.3 must be 0.6. Oh, yeah, because it doesn't work that way. I know that X is the change, but I need to use twice as many B's as A, and so the difference between this, I have to use twice as much. So even though it's the same difference, in order to make my equation work, I have to use twice as many B's compared to A's. Maybe? No. Okay. JT. Oh, this is from the homework tonight. This is the exact question off the homework tonight. Yeah. I have that one coming up. We'll do this one first, then we'll do that one. Because it makes an assumption that it doesn't tell you that it's making an assumption about. Alright, so now if I have these equilibrium concentrations, and I'm still looking for K, what do I know that K is equal to? Products over reactants, right? So it's going to be C over, what am I missing from my equation about K? Right, that needs to be squared. Now I know C is equal to 0.45. Everybody, something like that. No unit. Unitless. Okay, so that's one way I could ask. In fact, that is, you're going to have different values in your homework because it's randomized. But in general, that's how you do it. Alright, let's look at JT's question about whether they don't give you as much information. Unless there's any other questions about this one. Okay. Alright, so let's say I have this reaction. You can use different letters if you like. A and B are interconverting with C and D. Has a K equal to 2.1. Initially, only A and B are present, each at 2 molar. What are the equilibrium concentrations? Alright, so again, we need to make ourselves a table. Alright, so it says initially only A and B are present, and they give you the concentration. So if initially A and B are the only things present, what is the concentration of C and D? 0. Alright, given that the stoichiometric ratio is 1 to 1 to 1 to 1, how many x's should A lose? Right, just negative 1x. What about B? Same thing. How many x's should C gain? And the same thing for D. Alright, so then my E column, I just, add up what I have. Because it says initially there's only A and B. So there can't be any C and D initially. Yeah. Jordan. Mhm. Yeah, the change is just a ratio coefficient. Right. Alright, so we need to find, they gave us k this time. So what needs to go in the top of my k fraction? Yep, c times c. And then a and b go down here. Alright, what's one thing I can do right off the bat to simplify this? Right, I am going to take square root. I'm going to make it look more obvious why. Alright, because now I have x squared over 2 minus x squared. So a simple math thing I can do to make that work out Alright, so I'm saying I have this. I take the square root of both sides. So what's the square root of 2.1? You could certainly have solved it, which we'll do in our next problem, quadratically. That'll be our last thing to say. Alright, so now what do I need to do to get the x's by themselves? Yep. Okay, so I do 1.5 times Alright, now what? Okay, I can do that. Then what's my last step? Divide both sides by 2.45. Depending on how you chose to round. 1.18, 1.19, somewhere in there. So the question is, that is x, so what concentrations do those tell me about? Right, so this is 1.18, and this is 1.18. What's going to be the concentration of A and B then? It's going to be 2 minus 1.18. So this is where the problem is tricky, because they asked you, what is the final concentration of A? So even though you find X, you just go back up to your original table and plug it back in. No, in the homework it asks about just one of them. It says just A or... Yep. Alright, we ready for the challenge problem? As ready as we're going to get? The challenge part's the algebra, yeah. Hopefully everybody loves algebra. Oh, okay. Alright, so let's say Alright, so here I have this equation. I have PCl5 in interconverting to PCl3 in some fluorine gas. I know the K. And I want to know about the equilibrium concentrations of everybody. Alright, first thing, is this a balanced chemical equation? Is this a balanced chemical equation? Yes, check. Good. It should always be. Sometimes I make a typo. So that should be the thing you check first. Yes. Good. I'm not trying to trick you like that. Alright, so let's set up our ice chart. Oh, don't say you hate ice charts. Yeah, no. It's actually, I can hear just about everything from up here. It's very acoustically good. We're going to be doing ice charts for like the next 6 weeks. So, because this is just regular stuff. Then we're going to do acid-base ones, and then we're going to do something called an IACE chart, where we do titrations. Oh, I love them. I love them. They're great. Yeah, I mean, they don't have graphs per se, but it's a table, which is a close second to graphs. So, yeah, we're making buffers a lot of times. Which is what we're going to use them for. Buffers. Alright. So, initially, it says you have this. Does it tell you anything about the other two concentrations? They are assumed to be 0. Alright, because you assume you only put in the reactant. So what value of X should I subtract from this spot? Because it says it only has this in it. If it doesn't tell you the other two things, they're assumed to be 0. It's saying you only put in the reactant, and then after time goes on, things are going to happen. Yes. Alright, so just like we had before, right? Minus X plus X plus X. Then we add down. Alright, so now I need to figure out how to solve for X. So what would the K be equal to? Right, so I have something like this. X squared over 0.3 minus X, which equals 1.2. Is there any simple way to solve this? Can I just take a square root? No, so we're going to look at some... Right, so just factoring things out. Alright, so I have 1.2 times 0.3. What does it look like we're heading to? Quadratic equation. So what does the quadratic equation have to be equal to for it to make it work? It has to equal 0. And it's easiest if the x squared is a positive number. You could certainly do it the other way and have a negative x squared. It's just trickier. Success! We're at a quadratic. Alright, just as a reminder, right, we're in the form of ax squared plus bx minus c. Right, and you solve it using this. Right, familiar. You'll get one bad answer and one good answer. Alright, so plugging the values in up here. I have eagle ears from being a parent, I think. I'm not spying. I mean, you're talking out loud. Alright, so just plugging in the A, the B, and the C. It's just going to be tedious. We're going to get to the point where I can show you some shortcuts. Alright. I put the wrong values in here. Let's make it this. Oh, okay. No, that's right. Alright, you get down to a final answer where you get two options. At this point, you need to stop and think. What is X telling you way back up here in your chart? What units would X have? Which is molarity, right? Looking at your two options, can you have a negative molarity? Only if you're like on Star Trek and there's some sort of dark matter pulling moles out of the beaker. So no, the answer is no. Which means there's only one reasonable answer, which would be that. No. I mean, not in regular chemistry. In like weird theoretical physics chemistry, sort of. Yeah. Alright, so then you just plug it back in, right? This would be 0.245, 0.245, and this would be 0.55. Alright, we'll do more Friday. Lots more of these. Lots and lots and lots more.